Okay, this is the first video in the modeling section, and this is just an introduction to modeling. So what is modeling and why do we do it? Oh, here we go. A mathematical model describes a system by a set of variables and a set of equations that establish relationships between the variables. That's from Wikipedia. Okay, so we're looking at some kind of equation that connects a couple of variables. We should say that if we're looking at A-level, that's what these videos are primarily aimed at, then we're generally talking about equations, or one equation with two variables. Now, why would we do this? Well, really, we're looking at situations, systems which are probably quite complex, and we're really trying to simplify this down into the relationship between two variables, possibly the key variables involved, but there may be other parameters involved. But we just want a simple relationship because that's going to help us do some predictions which potentially may have some inaccuracy about them, but will be useful for whatever purpose. Okay, so if we just have a look at simple example here, say we're trying to model the relationship between daily ice cream sales. Imagine you've got an ice cream stall and you're selling ice creams, and the temperature. Intuitively, you think, well, it's warmer, you're going to sell more ice creams, and so we may have some notion about the fact that there's just a linear relationship between these. So, and this is described by this line. So we might sort of conjecture that there's a linear relationship. Let's say, well, let's form a linear model. Now, there are lots of straight lines, an infinite number of straight lines, but straight lines are defined by 2 points. So if we have two reference points, and these in the modeling context are usually called boundary conditions, then we can actually specify this line. We only need 2 points to know the equation of a straight line. So so there we go, those two boundary conditions. Okay, so that is a simple example. Let's just go over here and have a look at the different kinds of models that we might be looking at. Now, I've used t as the independent variable here because very often these models are time-based, not always. And this one, for instance, is not time-based, but very often they are. So could be t. We'd use t if it was time. We'd use x or something else if it wasn't. Y is just some generic variable, could mean all sorts of things. So this is basically the form of a straight line. Now, the y and the t are the variables. These are what we're trying to establish a relationship with. If we just conjecture that it's a straight line, we don't perhaps initially know what a and b are. So these are unknowns. And this relationship here is not really of any use until we actually can find out what a and b are. So if we have those boundary conditions, those two examples, if you like, of what x is when y is something else, so x-y pairs, then we can resolve these unknowns. Okay, so so that will be a nice straightforward linear model. Now, what happens if we think, well, this is not, we seem to have got sort of, as we increase the independent variable, it seems to kind of accelerate away, or maybe it sort of slowly decays down to a y value of 0, then we might be interested in something which is not a straight line, but possibly a curve. And yeah, okay, so there's different things that we could use to model. One is a quadratic. So it would be something of this form. Now here we've got A, B, and C, so we've actually got three unknowns here. So we would probably need three boundary conditions in order to resolve these. But we could use that. Then we have the exponential model, which is potentially of use in certain circumstances. Tends to be when the size of some population grows at a rate which is proportional to its size, sort of thing you might see in infectious diseases. As more people catch it, then it starts to accelerate away and growth happens very quickly. So that might be something of this form here, E being Euler's number here. So that would be an exponential model. Exponential models don't just have to look like this. They might be something like this, for instance, where we're not using Euler's number, we're using some other value, and this it might be to the power of something which is not just a straightforward KT, but might be something more complicated, maybe quadratic. And then maybe with a constant on the end. And in fact, if we look at this curve here, rather small, that describes this function, which we can see is of this sort of form. We've got an A of 0, an R of 10. The F of t is this thing here. And then our constant at the end is 1. So we've got a curved thing, but it doesn't carry on curving and going upwards like an exponential model. It sort of reaches a peak and comes back down again. Okay, so that's that's a possibility. The only thing you would say with, if it's a model, your model needs to be probably something relatively simple. It depends on how, what uses you're putting it to, and so on. But if it gets too complicated, then it may not be a useful model anymore. We have sinusoidal models. So something of this form looks rather complicated, but typically in the examples we see with this, then we won't have all four of these unknowns in, maybe a couple, and we'll have to resolve for those two. If you've looked at the videos on transformation of graphs, then this sort of form of thing might be familiar to you. So what else can we say? Log graphs, we use log graphs as well, because these could be useful, because if we take this kind of relationship, and if we take the in this case the natural log of both sides of the equation, then we get something that looks like this. Well, exactly this, in fact. And this, of course, looks very much like a straight line with y equals AT plus B. To kind of reassign the letters, obviously. So so actually it starts to look a little bit like that. Oh. So that is very useful in certain circumstances. It means we can actually, usually when we're drawing graphs rather than drawing an exponential graph, which tends to need quite a lot of space on the paper, you need a very tall page potentially. In this, but if we convert it in this sort of way, we can actually draw it as a straight line graph, much easier to draw and interpret and so on. That's quite useful. We also have differential equations, which if you've done any calculus, you may well have seen, but something of this form. And this actually is something that represents the rate of change of graph of some population, some dy, whatever it is proportional. This is a constant of proportionality to to the size of the population. And so there may be problems involving these. Now, if we want a relationship between y and t, then we would have to use calculus and integrate. But not all problems like this actually require us to integrate, because sometimes we're not actually asked for values of y, we're actually asked for values of the rate of change of y. So we can sort of see this as a kind of almost a separate variable. So there we go. So what do? We need to identify a type of model. Very often in the questions that you're going to be seeing, that you'll be told what kind of model it is, and if it's not told explicitly, then it should be fairly evident from the problem as to what kind of a model we're talking about. We probably need to resolve unknowns using boundary conditions. Initial conditions are just a special case for a boundary condition in time-based problems where t equals 0. In this case here, it'll give you the value of y when t equals 0. So that would be an initial condition. And one thing to note is that in the problems that arise, the boundary conditions are not always explicitly stated. They might be implicitly stated, not explicitly stated. It's just, things at rest. Something starts from an at-rest position, means when t equals 0, v equals 0. Velocity. So you often have to be able to look at the question and actually determine what the boundary conditions are that arise from that. And then once we've found our unknowns, we have a fully resolved equation, and we can actually use that then to, first of all, determine y, in this case from t, just by substituting a value of t in, or sometimes, or potentially, usually, in fact, t from y. And to do that, we need to sort of invert the relationship, which might involve changing the subject of the equation. And in the case of exponential equations, exponential relationships like this, we may need to take, well, in this case, will be the natural log of each side, so we can move t from the argument of a function on to the subject of the equation. So that is usually using your exponent log rules. Now, the other thing to say, I think, is simply that such models are usually useful within some range, and outside that range, then they will start to fall down, because the underlying assumptions basically no longer hold. And again, just going back to the infectious diseases situation, these things grow exponentially at an early stage, but eventually other things start to happen, like immunity sets in, or population runs out of resources for growth of a colony of rabbits. They run out of food. There's reasons like that. So they work well within an interval, but eventually we go. We take the independent variable too high or too low, then they get less and less accurate. Okay, so that basically is about modeling, and it's and we will see linear, quadratics, exponentials, all these coming into the problems that we're going to see. I think I probably just want to say one other thing, and that is to relate this back to what we do in statistics, because we've got a similar kind of parallel situation in statistics. And if you kind of recall back to what you've previously done, where we're looking at finding a relationship between X and Y, and we've got lots of data, and we've got lots of XY pairs. You've plotted this on a graph, and then you will have drawn a line of best fit that sort of seems to go fairly through them all, so that, you know, it's not too near the top ones or far away from the bottom ones. So it's got a fairly sort of you know, fair path through all these pairs which we've plotted on the graph. So that's your line of best fit. Now, in statistics, then, and in order to find out more about this, if you look at the videos in the data section, then you'll see that we do this rather more scientifically. And in actual fact, what we will do using our calculators is find a way of minimizing, if you think about the total distance of these points from the line vertically, then to minimize that total distance. And that's what we aim to do. So we go through our process on the calculator that finds the parameters, finds A and B, and this is also tied in with the concept of correlation. But you know, we can put those points into the calculator, calculate A and B, and that gives us the equation of this line, because A and B are the intercept and the gradient of the line. So that states it explicitly. Now, similarly, we may put all this data into our calculator, different set of data here, and with look at it, go, well, actually, it doesn't really look like a straight line, does it? Let's imagine, let's assume that this is an exponential curve. So we want to fit an exponential curve to this. So in our calculator, we can choose, let's say, this option. So this is similar to what we saw before, isn't it? A times e to the power of bx. So if we choose this option and press the option button, then it'll basically give us this in our regression model. So it'll give us our A and B values to substitute in there. So we then have a fully resolved exponential model. So this would be what, 6.7, y equals 6.7 times e to the power of 0.69 x, roughly speaking. Okay. So that's what we do. Again, we get our correlation coefficient. So correlation, I built it from data which had high correlation. So, but that's something for us to worry about in statistics. But I think it's just the point here that we're actually doing a similar thing in statistics to the modeling. The only thing is that our ways of actually determining A, B, or A, B, and C are slightly different, because in the statistics case, we're actually using lots of data points to do it. In our modeling, what we're doing is we are using boundary conditions to resolve for the unknowns. Okay, so right, well, hopefully that's been useful. I will be following this up with worked examples for all those example types on the previous page, because whilst they all got a lot in common, there are some essential differences as to how you actually tackle the problems. Okay, so hopefully that has been useful and interesting, and I will see you next time.